Let's take a close look at how Galaxy's Edge lightsaber blades work. So if we open up the base of a blade, which can be a little difficult to get into at times, we will see a couple of interesting things. We have, well, let's get a little closer. We have a string of RGB LEDs that run all the way up the length of the blade. You can see these three little dots, one on one side, two on the other side, with each RGB LED. That is a current limiting resistor, one for each color, red, green, and blue. And each goes to one of those pins coming out of the RGB LED. The fourth pin is power. Power comes in through that power pin called the anode, and then comes out through one of those three other pins, depending on if it's been turned on. How is it turned on? Well, down here at the bottom, we see this other PCB that's connected to the strip of RGB LEDs. This is the, well, what I'm going to call the logic PCB, or the controller. This controls turning the LEDs on and off, and we have 7 pins here, or 7 contact points between the controller and the strip of RGB LEDs. And we also have 7 of these rectangular things with 3 pins coming out of them. Those are transistors. When they turn on, they allow power to flow through them, and they're connected to the strip of RGB LEDs. So when the red channel turns on, power flows in through the LED and out through one of these transistors that's now been turned on to ground, completing the circuit, allowing the red LED to turn on. How bright it is controlled by that resistor. So we have 3 transistors here that control the 3 colors in each RGB LED. Then we have 4 transistors over here. These control the different segments of the blade. There are 4 segments of LEDs in this strip of LEDs in the blade. They control power going into the power pin for each segment. So if you only want a quarter of the blade to turn on, you only have to turn on one of these transistors here, and then power will flow into the power pin on one group of these RGB LEDs, and then it'll flow out through red, green, or blue, depending on which of these transistors are turned on, completing the circuit and making the color show up. So what turns these transistors on and off is under this blob of epoxy here. It's a microcontroller, and it's running some code on it that's interpreting commands that come in from the hilt, and then turns on the transistors appropriately to set it to whatever color the blade should be. And then it'll use those 3 transistors to set the color. And then when you're turning the blade on and off, you'll notice it ignites one segment at a time, or it extinguishes one segment at a time. That's the microcontroller turning these 4 transistors at the top on and off in sequence to produce that effect. So that's the basics of how the blade is controlled, or how it operates. But it would really be nice to actually see it in action, to really get an understanding of how the blade works. And to do that, what I'd like to do is I want to look at the signals being sent into those transistors. I want to see the blade turning on. I want to see the blade turning off. Maybe we can even see how the data that comes from the hilt to the blade, how that works too, or what does that look like. So I'm going to hook up a blade to this. This is a logic analyzer, a very inexpensive one. And the idea is you can connect up to 8 different signals to this logic analyzer, and then hook it up to your computer via this USB port here. And there's a piece of software that you run on your computer, and it will let you look at the logic levels of all the signals coming in on those pins that you've hooked up. Logic levels are going to be either low or high. It's not going to measure anything in between. So we're looking at it's either on or it's not, or it's off. We're not looking at is the voltage level on some pin somewhere 2 volts versus 2.5 volts or anything like that. It's not going to be that fine grain of measurement. It's just on or off. Is the pin on or off? Is the transistor on or off? So here is a controller from a blade, and what I'm going to have to do is each transistor has a pin on it that is connected to a microcontroller, and that's the pin that tells the transistor to turn on or off. So I need to wire my logic analyzer up to one pin on each of these transistors, which these things are tiny. But after quite a bit of work, I did sort of get it working. These wires here are all taped down because I've got just a few strands of wire going into these tiny little resistors here, so I could see the signals going to the segments. Unfortunately, the way those transistors work for the segments, they're PNP transistors. I can't connect just to one of those pins there. I need to connect to one of these 4 resistors, these tiny little specks down at the bottom here. I need to connect to one of those. But I did that, and so now what I'm going to do is take these wires here that you can see that run off from it up to these pins here, and I can start plugging them into my logic analyzer here. Now, this obviously isn't hooked up to actual LEDs here, but that's okay. I don't care about seeing the LEDs turn on. I just want to see the signals. And to hook this up to a lightsaber hilt like this, I have this little thing. This is a blade interface here, this little base package here, and this PCB that I bought from Dead Bothan Society on Etsy. This is a 3D printed case meant to match the case or the container in the base of a stock Galaxy's Edge lightsaber blade, and it's got 3 contact pads here that you can then wire stuff up to. So I have 3 pins coming out of it, and I can just take these and connect power and ground and data up to the stock blade, and this will provide power, ground, and data to the blade. So let's do that real quick. Ground to ground, like so. Power to power, like so. Now, for the data connection, I also want to snoop in on that connection. So what I am going to do is leave the connection just a little bit exposed like that. And then I will use one of these little things to just sort of grab onto the pin there, and hopefully that will be enough to read the signal being sent between them, something like that. So we'll find out in a minute here. So I'm going to wire this all up and then jump onto my computer, and we will watch the signals coming out of a lightsaber. I have everything wired up now. There's a small change in how everything is wired up. I need a ground reference. Otherwise, it doesn't know if the signal is high or low, because it doesn't know if it's high or low in reference to something. So you need to include a ground connection. So that means the ground pin here needs to connect to the ground coming out of the lightsaber blade, which means I would need another clip to hook up to the ground wire here. So instead of doing that, what I've decided on is just to use this tiny little breadboard here as like a little junction box. So power, ground, and ground and the data wires come from the hilt into this little breadboard here. And then coming out of it, it goes to the blade controller, which is over here. And another set of wires go to the logic analyzer. So that is how everything is going to be wired up. So now it's just a matter of putting this in the hilt, powering it up, plugging this into the computer, and starting up the software on the computer so we can take a look at exactly the signals going through a lightsaber blade. Here is the Logic Analyzer software. I have the Logic Analyzer plugged into my computer. I've put a white crystal into my Savvy's Workshop lightsaber hilt so we can see all the colors operating at the same time. I am now going to start recording data, and I'm going to plug the blade into the lightsaber hilt, and now I'll turn it on and then off. And that should be all we need. I made the blade clash a couple of times as well, just to add some extra data that we can look at. So I'm going to zoom out here, and here we can see all sorts of interesting things going on. So let's zoom in and take a closer look. Down at the bottom here, this is the data line, and you can see the data command being sent to the blade. The first three steps there, this low and then a high and then a low, those three steps, that sort of wakes the blade up, lets the blade know that there is a command coming in. And then that's followed by 8 bits, 8 ones or 8 zeros, or a combination of ones and zeros. And the way the ones and zeros are determined is for how long each, the length of period or the time that it's high. So that would be like a 0, 0, 1, 0, 0, 0, 0, 0. So then once that command is sent, I mean, you can see as soon as it drops to low here, lots of stuff starts to happen. You can see segment 1 starts to turn on. And you can see it's on, off, on, off, on, off, on, off, or the other way around, actually. For segments, when it's a low, because of how the transistors that they're connected to work, low is on for the segments. So it's on and then off, on and then off, on and then off. It's doing this at, and if you look here, 50% of the time. If you look at the little blue icons with text in them, just up and to the right of where my mouse cursor is here, one says F. That's the frequency of this signal. So every 200 times a second, there is an on period and an off period of this signal. 50% of the time it's on, 50% of the time that's off. That's called the duty cycle, which is the next little section there, the next blue background with white text thing saying duty there. It's referring to the duty cycle of that PWM signal, that pulse width modulation signal. So when you hear of pulse width modulation, it's literally pulses of electricity, which you can pretty clearly see here now, looking at the logic analyzer. So what's happening is when the blade turns on, it goes through that ignition sequence where one segment at a time is powered on. And for white, when it first turns on, the segment fades in. It starts at 50% brightness before then going to 100% brightness. And if we look at all 4 segments here, you can see as segment 1 goes to full brightness, segment 2 turns on at 50% brightness. And then when segment 2 turns all the way on, segment 3 goes to 50% brightness. And then segment 4, there is no fading in effect. It just immediately turns right on. And we can even measure how long does that segment remain in that faded state before it turns on. Set up these timing markers, and I can see it's about 75 milliseconds here. I believe it's actually closer to 85 milliseconds. This is just from previous testing that I've done that I'm pretty sure it's 85 milliseconds. Yeah. Okay. So what else can we see here? We can see the red, green, and blue channels. And we can see that they're also pulse width modulated, but at a much higher frequency. We can see they're being modulated at 6 kilohertz. And you can see when all 3 colors are on to produce a white, each color is the PWM signal has a 43 or 44% duty cycle. So the red, green, and blue LEDs in your blade, when you have a white crystal plugged in and the blade is turned on, all of them are running at about a little less than half brightness. And the reason that's happening, instead of making it super full, all 3 colors on, is one, it's going to eat up a lot of power and it's going to go through the batteries very quickly. And the second reason is if white if all three of those colors were on when you had a white blade, the white blades would always be brighter than any other color because you have 3 LEDs on all the time instead of just 1 or 2 for all the other colors. So you have to turn down all 3 red, green, and blue LEDs so that way the brightness of the blade as a whole is similar to the brightnesses that you will see in other blades. And then we can see here, periodically there is a data command being sent to the blade, and we can actually time those. And we can see that less than once a second, there's a command being sent to the blade. And what that command is, it's telling the blade what color to be. This is sort of a backup or a just-in-case feature built into the way the hilt and the blade operate. So if the blade temporarily becomes disconnected, if it moves around in its socket that it plugs into, and it loses a connection, then the microcontroller won't know what color it's supposed to be, and your blade will be stuck off until you turn it off and on again. So what they're doing here is they're sending a command, note you're white, turn on white, turn on white, turn on white, less than every second they're doing this. So that way, if the blade does lose connection momentarily, and then it makes that connection again because it's wiggling in the socket, it'll immediately turn back on white. And this particular command, you might remember from the turn on command we saw earlier, this command is a little bit different. And the reason it's a little bit different is because this command isn't saying turn on, it's saying immediately become this color. Don't go through the animation process. Don't ignite, just immediately every segment turn on this color right away. And if the blade is already on, it ignores these commands essentially. So if we move a little further along, we can see that there's this weird gap here. And we can see the PWM of the color channels is different. We can see blue suddenly turns off, but the red and green are essentially both always on. That's a yellow color. This is a clash event. This is when your blade stops suddenly or hits another blade. The lightsaber produces a little extra sound. The blade flashes, and then it goes back to normal. This is a clash. And here you can see that those 3 long low, high, low signals to let the blade know, hey, there's a command coming, followed by the command. And in this case, this command is saying, okay, it's time to clash. The blade has stopped short or it has hit something. Go through your clash animation. So this is the command for clash. And the blade immediately kicks over to a yellow color. And it holds that color for, well, we can time it real quick. It holds that color for about 40 milliseconds. And then it turns back to the color that the blade is supposed to be. In this case, white. And you can see I did clashes a couple of times here. And you can also see here, this is one of those, hey, you're still white, turn white commands immediately follow just by happenstance that I happened to make it clash at the same time that it was trying to send one of these, hey, stay on commands. And then we get to where I turn the blade off, and we can see here is the command to turn off. And you'll notice that there's a pause before it starts to turn off. And different colors have different times, different pauses before they start to turn off. I'm not sure if that's just because of the sound effect that's being used. Some have a longer or shorter turning off sound effect, and so they had to put different timings into the blade, or if there is some other means or reason for it. But here you can see there's about a 300 millisecond pause here before the blade starts to turn off. And if we look closer, we can see it actually has a slightly different sequence in turning off than it did turning on. We can see it starts to fade out, but the duty cycle here is now, well, it's 33% off, 66% on. You have to keep that in your head, that off on these segment lines. When the signal is low, that's when the blade or the LEDs are on. So it says it's a 33% duty cycle. It's 33% off, 66% on. So it's starting to fade out, but it's fading out slowly. And then it jumps to 66% off, 33% on. So it's a two-step fade out animation. So it's always on, then it fades out a little bit, it fades out a little bit more, and then it's off. So 2 steps between on and off, whereas there was only 1 step when it was turning on. And in fact, different colors have slightly different turning off animations, different timings, different sequences of brightness that they go through as they turn off. Again, I'm not sure why different colors have different ways of turning off. I don't know if that's, again, down to length of the sound effect that they had, or if certain colors, I don't know, were special. I have no idea. And then once the blade is off, there's 2 commands sent, and we can see they're the same command. And this is a command to sort of tell the blade, okay, you're really off now. Don't do anything until I tell you to ignite again. What's happening is these commands here to just turn on and be this color, or other commands, the blade will accept them once it's turned on. But once it's all the way off, this command's telling the blade, okay, you're off. Stop accepting commands. Don't just turn on some random color if you get that signal. Wait until you receive the ignite command again. So that's a look at how the blade works. Now I'll try a different color here, and we'll see what that looks like. We'll try, say, yellow, for example, because yellow will have 2 colors, red and green. So I will go and start capturing data, turning it on. Okay, that should be enough. I threw in a couple of clashes there so we could see that happen. Let's take a look. So just like we saw before, there is the on command. This will look a little different than the white one. You'll notice, if you're paying close attention, that there are 8 bits being sent through this command. The first 4 bits identify the operation, turn on, turn off, clash, whatever. The second 4 bits identify the color. So the first 4 bits, this, what we'll call here 0010, should be the same for the power on in the white sequence, and we could actually go over here and take a look at that. 0010. And the next 4 bits, 0000 for white. For yellow, we have 0011. So that would be a 3. And if you were to map all these commands out, or the colors, I should say, you'll notice it's sequential. So 0000, this is in binary, that would be a 0 for white. 0011 is 3 for yellow. 0001 would be red. So 0 is white, 1 is red, 3 is yellow. Well, what comes between red and yellow? Orange. And if you have an orange Kyber crystal, or if you have a Kyber crystal with an orange RFID number on it, it will send 0010 as the color, orange, to the blade. Unfortunately, stock Galaxy's Edge lightsaber blades don't ignite as orange. They will ignite as yellow if they're sent the orange command. So we'll go back to the, we're looking at yellow here, and then it goes through that power on sequence again, 50% duty cycle, 200 hertz as each segment turns on. The last segment just turns immediately on. We see the pulse width modulation here of the red and green channels, and then we will see a clash. And we can see the command for the clash is being sent here. And when the command is received, we can see the blue channel turns on. the PWM duty cycle doesn't change, or it does change. You can see here it's 60%, and then when the clash begins, it drops to 50%. And all three channels turn on to produce a white flash at 50%. And then it turns off here, and the PWM signal goes back to 60% on. So the red and green channels reduce in color or brightness a little bit as the blue one turns on, again, to sort of keep the blade, all the different colors, of a somewhat even brightness. So there's a couple more clashes here, and then it turns off. And here we can see the yellow power off sequence is much different. So we'll look at white again real quick, where you can see how each segment sort of drops in brightness 2 steps, 66% brightness, 33% brightness, and then off. But on yellow, the fourth segment, that's the segment at the far end, at the tip of the blade, turns off immediately. Segment 3 immediately drops to what looks to be 33% brightness. And then the second segment, that's the second segment up from the base, that starts to turn off at 66% brightness. So as soon as you turn yellow off, it has a completely different shutdown sequence where it immediately turns off. Look at the delay between the shut-off command here and the blade turning off. It's immediate, whereas, again, we go back to white, we can see that there's a delay between the shutdown sequence and it starting. So white takes a little while to turn off, yellow turns off immediately. It's probably not something you've noticed if you have a Savvy's Workshop lightsaber blade, or lightsaber, how quickly the blade extinguishes and how that time is different between different colors. But now that you're aware of it, you'll probably notice it every time. I'm going to put a red crystal in, and I'm going to start capturing that. Now, if we look at this, zoomed out a bit, we can see clearly the red channel is always on, the other two are not, which is expected because it's a red crystal. And one other thing to note about red, here's the shutoff command. Here's where the command, or where the blade starts to shut down. There is a massive, massive gap of time here. Nearly a second, 850 milliseconds between the time it receives the command to turn off and when it executes the command. So in terms of blades, from what I've found in my testing, red takes the longest to turn off, yellow takes the shortest to turn off. Now, since I ignited a red crystal here, we can go back to this power on command, and we can see what I was talking about earlier about the 4 bits that represent the color. We see 0001, so white has a value of 0, red has a value of 1, yellow has a value of 3. So, what if I take a kyber crystal that has an orange RFID number in it, and I use that? Start capture. Okay, so that was a orange kyber crystal. Let's take a look at the power on number here and see if we can see what I was talking about. So we have our 8 bits here. These last 4 bits represent the color 0010. That's a 2. Orange has a color value of 2, or it's being the command with a value of 2 represents turning on as orange. So the hilt definitely supports orange and cyan. The blade just doesn't. And I want to fix that. Which is why I've been staring at screens like this for weeks now, at least, to getting all the timings down, getting this power on and power off sequences, figuring out how fast it PWMs the different color channels, depending on which crystal has been inserted. All of this stuff I've been staring at, trying to study, trying to document, so that I can go ahead and make my own blade controller using the stock LED strip that's in those blades, and just replacing the controller such that the new controller will respect those orange and cyan commands. And then maybe I can throw in a few extra special effects just because I can at that point. So that's the goal. That's the ultimate plan here. That's why I am looking at lightsaber blades and how they operate, because I want to make my own blade controller. So maybe you found this interesting. I hope you found this interesting, learning all about the minutiae of Galaxy's Edge lightsaber blades and how they operate. I think for anybody interested in creating their own blade controller for Galaxy's Edge lightsaber blades, this information should be really helpful. Good luck. Have fun.